How many unique points do you need to constrain a line? How many unique points do you need to constrain a plane? If you have a certain number of unique points, then how many total lines, unique lines, can you make through those, going through those 3 points? Same idea with a plane. And for that matter, what does the term unique even mean? Unique points, unique planes, etc. And how does this all tie in with the term dimension? So, we've got 3-dimensional space. There's different dimensions. What does that even mean? Okay, well, first of all, one thing to note is that, so imagine you're a caveman, cavewoman. You go outside and you're observing the physical world around you, and you're noticing there's different phenomena, physical phenomena that, you could consider trying to quantify or measure. And, there's a lot of different things you can measure, but there's three fundamental phenomena. Is length, so like space between points, there's time, and then there's weight. So things are being pulled towards the ground, which we now have a more advanced understanding of. So we call that mass. But as a caveman or cavewoman, you would be noticing weight, not mass. But so those are 3 fundamental phenomena. But if you think about it, though, length is unique. It has an aspect that time and weight don't have. Okay, so as we know, length, to specify the location of a point in space, you really need 3 distinct kind of character attributes to describe that point. You have to say, you can't just put one figure. You really need 3 distinct figures to describe that point. Because, right, there's no way, so in terms of the Cartesian coordinate system, you go, this direction, this direction, this direction, and now you've described the location of that point in space. But it's not just the Cartesian coordinate system. For any coordinate system, you're going to need 3 distinct figures to describe the location of that point in space. But when it comes to time or mass, if you wanted to describe if there was something here at this point, an object or something, and you wanted to put a descriptor of that point in terms of time, well, there's only one figure you need. I mean, however you want to put it, in terms of the time of the day, or I guess relative to the history of the universe, I don't know, but you really only need, there's only one figure that you need. Time is one-dimensional to us, from our perspective, and same with mass. But space is clearly 3-dimensional, okay? So that's the idea of when we're talking about the dimension of something. And so a point, okay, we call a point 0-dimensional. Because technically this point has no size. When you say a point, it has no size. So there's no measurement of this. I mean, it has location in space, but talking about the point itself, just looking strictly at the point, it has no size. So there's no measure. As far as space, there's no measure. So there's no dimension. Okay, then we call a line 1-dimensional because it takes one figure to describe the length of this line. And with a plane, it takes 2 figures. And then with a solid object, it takes 3 figures. Okay. Now, we know from, stated as a postulate, that if you have 2 points but not the same point, then that's going to define one unique line in space. Now, if you have 2 other points, or if you have another point, so now that's 2 unique points, those are also they're said to be collinear. Any 2 distinct points are said to be collinear, and they define a unique line. These 2 points, A and B, and points A and C point A and C are collinear. Point A and B are collinear. So does that mean points A, B, and C are collinear? No, because they're contained on 2 separate lines. To be collinear, you have to be able to be contained on the same line. Okay, but you have 2 unique points, C and D, so points C and B are collinear. Okay, so now let's think about it. We have point A here. How many unique lines can we draw through point A? Well, there's an infinite number of them. Infinite. Right? That's why you need 2 points to constrain a line. Now, with 2 points A and B, there's only one unique line that you can draw through these 2 points. One and only one. Okay? And so now, if we're going to ask the question, how many lines can you draw through 3 unique points? The idea of unique means that It's not, if the points aren't unique, then there's no redundance in terms of adding more dimensionality. So if I put a point here that's collinear with A and B, well, then I haven't added any dimensionality by adding that point. I can't make a plane. I can't make any additional lines. So point C is kind of redundant in that sense. But if I add a point that's not collinear with A and B, now this is a unique point. It's distinct from points A and B. You started with point A, okay? Now, you could be redundant and put point B right at point A, and you haven't changed anything. Or you could make point B unique and add it off of point A. Now, any point you add off of point A is going to add dimensionality, and you're going to have a unique line, no matter where the point is, as long as it's off of point A. Now, from there, if you're going to be redundant, you're not going to add a point that's on another point. But you'll add a point that is collinear with A and B. That's redundant. Okay, but if you add a point that's not collinear with A and B, you've added more dimensionality. Okay, and so now we can ask multiple questions. We can ask, how many unique lines can we create through these 3 points? As well as if we go up one dimension to the next basic figure, which so in 1D it's a line, in 2D it's a plane, how many planes can we create through these 3 unique points? Okay, well, first of all, if a line, so you had one unique point, then you added another point, and that allowed you to create a one-dimensional line. So you needed 2 points to create a unique one-dimensional line. Then you can see that 3 points is going to allow you to create one unique 2-dimensional plane. So 3 unique points allow you to create one unique plane. Now, how many unique lines can we draw through these 3 points? Well, you can see it's going to be 3. But we can be a little more systematic about this and generalize this idea in that, so we've got these 3 unique points, A, B, and C. What we're trying to see is how many combinations can we create. So combinations just comes from statistics, right? But the order doesn't matter. So we've got 2 slots here. Okay, we can make line AB. That's a line. But line BA that's redundant. We don't want to count. The order doesn't matter. Okay, we can create line BC. We can create line AC. So what we're doing here, it's 3, choose 2. The combinations makes it, the order doesn't matter. And so the formula for this is you go 3 factorial over 2 factorial times 3 minus 1 factorial, or 3 minus 2 factorial. So it's 3 factorial over 2 factorial times 3 minus 2 factorial. So that's 3 factorial is 3 times 2 factorial over 2 factorial times 1 factorial. So 3 lines. And if we wanted to go back and see how this pattern started, so we started with a single point, and there was an infinite number of lines you could draw through that point. Then we added a unique point, and now you have one unique line. But, okay, to kind of parallel what we just did, with those 2 points, how many unique points can we create? Well, we've got 2 points. You see, when we just went up to a third unique point, we said, okay, how many unique one-dimensional lines can we create from those 3 points? Well, if we want to ask here, how many unique points can we create? We just have 1 slot, so it's 2, choose 1. That's going to be 2 factorial over 1 factorial times 1 factorial. It's just 2. It's still just 2. Okay, now how many unique planes contain a single line? Well, that's going to be infinite. In the similar way that 1 point is going to contain an infinite number of different lines, a line will contain an infinite number of different, one line will constrain an infinite number of different planes. Okay. Now, if we add an additional point that's not redundant, so it's not coplanar with the 3 initial points. It's like out here. Well, okay, how many unique points can we make with these 3 points? That's going to be 4, choose 1. It's going to be 4. How many unique lines can we make between these 4 points? That's going to be 4, choose 2. 4 factorial over 2 factorial times 4 minus 2, so it's 4 times 3 times 2 factorial over 2 factorial times 2 factorial. So 4 times 3 over 2 factorial is 2, so 6 unique lines. Line AD, line AC, AB, BD, etc. What about planes? How many unique planes can you create using these 3 points? So again, the idea is you've got A, B, C, D. These are all unique. So you're choosing. If there's 4 items, choose 3. But the order doesn't matter. So it's going to be 4, choose 3. If you did just 3 points, 3 choose 3 is just 1. 3 points contain 1 unique plane. 4 choose 3, you're going to have 4 factorial over 3 factorial times 1 factorial. So 4 times 3 factorial, that's 4 factorial. 4 planes. Okay, but now, what if we wanted to keep going? What's the next simplest object past a plane? Well, it's some sort of a solid, right? But unfortunately, it's not. It wouldn't be that simple. Like, okay, we could think about, all right, okay, how many unique objects, solid objects, 3D objects, can these 4 points contain? Well, again, this is not as simple because I guess you could say, all right, these are the vertexes of the solid object, and there's straight lines between the vertexes. Or maybe you could say that it could be straight lines or curved lines, whatever, as long as those are the vertexes. All right. So in that case, we would say you have A, B, C, D. There's 4 points. Choose 4 because you're going to need 4 points to describe a solid with those vertexes. So 4 choose 4 is going to be 1 solid object. Okay. So can we keep going from here? Let's add point E. Well, no, we can't do that. Why not? Because that we'd be going into the 4th spatial dimension. We don't know what that is or if it even exists. All right, now let's think about if we have 2 unique lines, then how many planes do those 2 lines constrain? Okay, now this is a little bit trickier because there's different scenarios we have to think about. So, okay, when it comes to 2 lines, how can 2 lines be related? And they're definitely different lines, so not coincident lines. They don't lie on top of one another. Well, they could intersect, or they don't intersect. If they don't intersect, then you have the case of parallel or skew. Then in terms of like dimensionality, that's really it. I mean, you could maybe say they're perpendicular or they're not perpendicular, but that doesn't really matter. So in terms of dimensionality, these are the 3 cases. Okay. Now, so if we've got 2 lines that intersect, they're not coincident, they don't lie on top of one another, then that's going to constrain 1 unique plane. Okay, so this would create 1 unique plane. And why is that? And it doesn't matter. They don't have to be perpendicular no matter what the angle is, as long as they're not the same line, then it's going to create a unique plane. Now, why is that? Well, because think about, so we've got a line, so that's 2 unique points. We can, with a line, we can make a dimensionality of 2. But now, since the lines don't intersect, if we're constrained to the world of these 2 lines, since the lines don't intersect, we can pick another point that's off the line. That's a unique point in terms of dimensionality. Now, we've got 3 unique points. That's a plane. Now, you might say, well, okay, well, we can make more than just this one plane. Well, no, if we try and pick, let's try and pick another point that we pick is going to be coplanar with the initial 3 points. We can't add more dimensionality if we're constrained to those 2 lines. Or I guess we could go, now that we have a plane, we could go off the 2 lines into the plane, but there's still, it's one unique plane in 3D space. Okay, and that's any intersecting line, no matter what. If the lines intersect and they're not the same line, then it's going to they constrain one unique plane. We could look at the origin here. Here's 3 lines. They all intersect. So, you get the X, Y, and Z axis. The X and the Y axis constrain the XY plane. Just now in this case, they're perpendicular, but that doesn't mean anything as far as constraining planes. You've got the YZ plane. You've got the XZ plane. Okay? All right, now let's think about non-intersecting lines. What about parallel lines? So let's see, we've got 2 lines that aren't intersecting. Well, I think the definition of parallel gives away the answer. It's 2 lines that are contained within the same plane that don't intersect. Okay, and so by that definition of parallel lines, you can tell that 2 parallel lines constrain a unique plane. One unique plane. You can't, not multiple planes. And why is that? It's the same idea as before with the intersecting lines. Okay, we can pick a point. There you go. Now we can pick another point. So we've got a line in this system here. Now we want to add another unique point where we can come to this line. There you go. 3 unique points. They're coplanar. But well, why can't we create a unique plane? Because we can't pick another point that's, if we're staying on the 2 lines, we can't pick a unique point. It's going to be coplanar. Or if we're thinking about maybe we can go into the plane, but still. So it's one unique plane. Okay, now what about 2 skew lines? So let's see. We'll have, and then one passing like underneath. Okay, so let's go through the process. We'll pick a point. Now we can pick another point. Now we can pick a 3rd point. So there's one plane that's constrained. But so now if we want to go in a unique dimension, we come out here, let's say. Okay, so now we know that we do 4 choose 3, so that's going to be 4. That's 4 unique planes, but that's it. We can't go in a unique dimension because the only direction we could go, we have to stay on these lines or move out in one of those planes. So before here, we had plane A, B, C, and these like line L and line M. So we had to stay in plane A, B, C, or if we could move out of the plane, in that case, we could do that because we could move along line M to get to D. So we started, this is kind of confusing. So, we started with line AB. We had the full line AB. Then we picked a point on line M, point C, and now we created this plane. Well, obviously that plane contained all of AB because we had already started with all of AB. So that plane contained all of AB. So we had all of line L and then this plane ABC that we could move along. So now if we had to pick another point, we had to get off that plane, which also meant we had to get off that line because that line was contained in that plane. We had to get off the line and out of the plane. Well, line M allowed us to do that. So now we pick another point D. Now we've got with C and D, we've got all of line M. So naturally, those four planes, we can move anywhere along the 4 planes that contain A, B, C, and D. The 4 unique planes. Well, those planes are gonna contain all of line M and all of line L. So now we need to pick another point that's not on line M and not on line L. Well, that's what we started with. So two skew lines are going to constrain 4 unique planes. Okay, so this idea of dimensionality and these looking at these different ways that lines, planes in 3D space are constrained. We could continue to look at this from different angles and dig deeper into it, and we'll continue to do that throughout geometry. But this should give you with what we just did in this video, you should have get your feet wet with these ideas.